So moving on to the second part of Chapter 1, I'm now going to discuss pleural pressure and how the dynamic properties of the respiratory system affect pleural pressure. And again, this will deal with the dynamic aspects of pleural pressure. The first part we talked all about the static aspects of pleural pressure with respect to the lung and the chest wall. So the dynamic aspects of pleural pressure will deal with the amount of the pleural pressure that is dedicated to driving gas flow. So I sigh a lot, I'm sorry. That's me collecting my thoughts. Until this point, we've only considered the lungs and the chest wall as being purely elastic. That is, without any pressure needed to overcome the frictional and viscous forces that occur during gas flow. But clearly, when we breathe in, we're moving gas from the atmosphere down deep into our alveoli, where oxygen and carbon dioxide participate in gas exchange and maintain our being. So in order to drive this flow, we must generate an additional amount of pressure to overcome these viscous forces. And again, this burden is placed upon the muscles of respiration, or when you're tubed, the ventilator. But we'll talk about that more in part 4 of this chapter. So again, these forces are represented by the tube in the tube and bag model of the lung, and this additional pressure is generated by the respiratory muscles is described by this equation. And as I think most, if not all of you realize, this is a rehash of Ohm's law, which uses an electrical analogy whereby the pressure gradient between the body surface and the alveolus is equal to the flow of gas multiplied by the resistance of the airways. So back to our friend, the bag and tube model of the lung. This is a static pressure that we talked about in part 1. This is described by the compliance. But then there's this additional amount of pressure that is added, and that's the dynamic pressure. And this is the pressure that is used to drive gas flow. And it's the pressure differential here is body surface pressure and the alveolar pressure. So it's the static pressure down here plus the dynamic pressure, which is equal to the gas flow multiplied by the airway resistance. So talking a little bit about the dynamic properties of the respiratory system, if airflow or the resistance is increased, so I picture an asthmatic or a chronic bronchitic or somebody with a large upper airway mass, we can imagine that if this resistance is increased, then a greater pressure gradient must be generated by the muscles of respiration to overcome this additional resistive workload. During an inspiration, the drop in pleural pressure, so this is, I get this question frequently from medical students, like what's happening when you breathe? When the pleural pressure drops, what are the sequence of events that are occurring? So it's hard to describe because everything is happening instantaneously. But if you can imagine, during an inspiration, the drop in pleural pressure is initially invested wholly in a drop in alveolar pressure, and this is what gets the gas flow moving. But also instantaneously, just as instantaneous as the pleural pressure is transmitted to the alveolar pressure, gas begins to flood the alveolus. So then pressure in the alveolus then begins to raise relative to the pleural pressure. And as this alveolar pressure increases with the precession of gas flow, the drop in pleural pressure then maintains the transpulmonary pressure and thus the static lung volume. And I have a bit of a hokey animation in a few slides, which I hope will clear that up a little bit. So how much additional drop, again, part one, we talked about the drop in pleural pressure that is required to maintain a lung and chest wall volume, the static pressure. The additional drop in pleural pressure required to decrease alveolar pressure and affect gas flow depends on the type of gas flow in the airways. This is probably a rehash of medical school for almost all of you watching this lecture, and that is this difference between turbulent and laminar flow. It's a bit of an artificial distinction in the lungs, which I'll talk about briefly, but here I've graphically depicted the difference between turbulent flow, which is flow here on the x-axis, and the change in pressure required to generate that flow on the y-axis. And you can see with turbulent flow it's kind of an exponential relationship. That is, as flow increases, the change in pressure is increasingly great. And turbulent flow is essentially almost always present in the large airways. And turbulent flow, which I talk more about in the written chapter, is density dependent, and that density dependence is what determines the Reynolds number, which the Reynolds number helps estimate where turbulent flow becomes transitional flow, becomes laminar flow. But again, the key point with turbulent flow is that it is density dependent, and it's, as I mentioned, it's almost in the large airways. It's dependent on the density of the gas, and it increases exponentially with flow, such that there's a dynamic effective resistance. That is, the effective resistance is constantly increasing with increasing in flow, and that is depicted by the increasing slope with increasing flow here. So essentially, for those of you who like calculus, you know, the effective resistance would be the basically the derivative of this of the equation that defines this line. Then there's laminar flow, which is essentially only exists in the very smallest of the airways, and that is there's a nice linear relationship between laminar flow and the change in pressure on the y-axis there. And laminar flows, as I mentioned, is only in the very smallest of airways, and it is viscosity. Sorry, kicking things over here. Laminar flow is viscosity dependent, density dependent, viscosity dependent. And the pressure gradient that must be generated increases linearly with flow, such that the effective resistance is constant as flow increases. And again, this tends to follow Poiseuille's law, which, if you write out that equation, which is in the chapter, is viscosity dependent. And some of the distinction is somewhat clinically relevant in terms of the application of heliox, which I talk more about in chapter 1. Heliox reduces the density of the gas, so it helps transition turbulent flow to transitional flow to laminar flow. Interestingly enough, though, a lot of people don't mention this, is that heliox actually has a greater viscosity than air. It has a lower, heliox has a lower density but a greater viscosity than air. So in theory, heliox should actually make laminar flow worse. But clinically, in reality, you probably, in severe asthmatics, you probably have turbulent or transitional flow all the way out to the most distal of airways. And so actually lowering the density of the gas probably helps these patients, even with very small airways disease. And both types of flow are very sensitive to changes in airway radius. That is, if you narrow the airway or lower the radius, you have an exponentially large increase in the effective resistance. So turbulent and laminar flow patterns were initially described in long, smooth, non-collapsing, unbranched tubes, which is an experimental model that is nothing like the tracheobronchial tree. So this application of Reynolds number to the airways is highly artificial. In reality, airflow is mostly transitional, which is a pressure differential somewhere between laminar and turbulent flow. It's often quoted that if the Reynolds number is above 4,000, then it's turbulent. If it's between 2 and 4,000, it's transitional, and there's less than 2,000, it's laminar. But again, that is it's essentially in a long, unbranching steel pipe that these numbers were derived. So in the human lung, it's estimated, and believe me, I was just as surprised to hear this or to read this, is that it's estimated in the human airways. In order to get laminar flow, you actually probably need a Reynolds number less than 1, not less than 2,000. And that's just a function of the distorted, rough, mucus-filled airways that define the human tracheobronchial tree as opposed to a long steel pipe. Because airflow can transition from turbulent to laminar flow during various inspiratory efforts, and because airways tend to dilate during inspiration and compress during expiration, the pressure-flow relationship in the lungs is additionally much more complicated than the previous slide that has a very nice exponential turbulent flow relationship and a very nice linear laminar flow relationship. So this is a graph of a cartoon of airflow dynamics in the lungs, and again, this is not the Campbell diagram. Please do not mix up the axes here. While the x-axis here remains pleural pressure, the y-axis here is airflow. It is not lung volume. This is a totally different graph. So keep that in mind. So this relationship would describe ideal flow through an ideal tube, and that is there's a constant resistance that is as pressure decreases, as pleural pressure decreases, there is an increase in airflow such that essentially you're lowering pleural pressure relative to atmospheric pressure. This increase in the pressure differential then increases flow, and the increase in flow is modulated by airways resistance, which is essentially the slope of this linear perfect line. But as you can tell by the way I'm saying this and by the last few slides, it is not nearly this simple in life. This linear relationship does not exist. So this is this nice relationship between the pressure differential in the alveolus and the body surface and airflow in the idealized situation. In reality, the curve probably approximates this much more than the nice line that has just faded into the background by fancy PowerPoint animation. So there's this initial increase in the slope, and that increase in the slope here would be a marker of decreased airways resistance. That is, you have a greater flow for a smaller pressure change, and this increase in slope relative to the idealized tube is the result that during early in inspiration the airways are tethered open. So there's actually this dynamic decrease in resistance as you're inspiring. But then as flow increases, the curve starts to bend a little more, and this bending of the curve down into the left is a representation of an increased effective resistance, and this is most likely the generation of greater transitional and turbulent flow at higher inspiratory flow rates. So this is probably more representative of the pressure-flow relationship in the human airways, as I mentioned, as they distend with inspiration and generate turbulent gas flow at higher inspiratory flow rates. So here, if you were to compare pleural pressure at this point, the flow through the idealized tube would be not as great as the flow is through these tubes in the lungs that are dilating as inspiration progresses. So that's what that little arrow represents. So this curve shift down and to the left would be a representation of an in vivo increase in airways resistance, which could be the result of a COPD exacerbation, an asthma exacerbation, or interestingly breathing at small lung volumes. It's very important, and I will describe a bit later in this talk that airflow is highly dependent upon lung volume, and that is because, as I mentioned, at higher lung volumes the airways are distended open, so that increase in airway caliber tends to increase flow at a higher lung volume. Conversely, at a smaller lung volume, you have an effective increase in airway resistance, which is what you see by the shift down and to the left. So with increased airways resistance or breathing at low lung volumes, as I mentioned, which tends to narrow the airways, a lower pleural pressure must be generated to obtain any given airflow. So that cartoon is depicted here, that to obtain this airflow here compared to this state or this state, right, the pleural pressure is much lower. So this patient would have to generate a much lower pleural pressure. The muscles of inspiration would have to work much greater in order to generate this gas flow to overcome the inertial and viscous forces of gas to drive airflow. And we will see in subsequent slides how this relates to the Campbell diagram. But it's important to realize that in states of increased airways resistance, increased turbulent or transitional flow, that a greater pressure differential must be generated in order to drive gas flow. So, to recap, pleural pressure must decrease in order to drive gas flow in addition to generating and maintaining lung volume, which was part one of this talk. When high flow or high airway resistance exists, then pleural pressure must lower to a greater extent to create airflow. At any point during inspiration, the pleural pressure is the summation of the pressure required to affect airflow as determined by the flow rate and pattern, and the resistance as I just described on that previous slide. Remember, the greater the resistance in the airways, or the more turbulent the airflow is, the lower the pleural pressure is required. And that's in addition to the pressure required to maintain lung volume based on lung compliance, and that was what the entirety of part one dealt with. So that will be illustrated by the following animation. And one way of thinking of it is, if the pleural pressure is like the total energy of the system, the pressure of the total energy that is required to drive gas flow is a little bit like the kinetic energy, whereas the pressure that is required to maintain volume is a little bit like potential energy. So if you remember from high school physics that in a given system, the total energy remains constant. The total energy remains constant, but there's this shift between kinetic and potential energy. So the classic example is the rock on the top of the hill, and it's all potential energy, and then it rolls down, and as it's rolling down the hill at any given point, less of the energy is potential and more of the energy is kinetic, until you get to the bottom of the hill when the rock stops rolling and none of it's kinetic and it's all potential again, depending on its height above sea level, I guess. So pleural pressure is the same thing in this kind of silly analogy, in that the pleural pressure that's generated at any given point during the inspiratory cycle, the pleural pressure is the total amount of pressure, and a certain fraction of that pleural pressure is distributed into the pressure required to drive gas flow, which is the dynamic pressure, and the pressure required to maintain instantaneous lung volume, and that's the static pressure. And that's what I hope to illustrate with this next hokey slide. So again, returning to the bag and tube model of the lung, I've tried to color coordinate it here. So the pleural pressure will always be green. The static pressure or transmural pressure will always be blue. and the alveolar pressure will always be red. And then body surface pressure and airflow will be kind of in this ugly orange. And down here we will see how the pressure changes with time. So let's take a deep breath in. So pleural pressure, the green, has decreased. The pressure here will decrease in concert. So immediately, and this is all instantaneous, this drop in pleural pressure is all invested into a reduction in alveolar pressure. So the alveolar pressure drops with the drop in pleural pressure. And you'll see that by the equivalent drop in alveolar pressure on this cartoon down here. Okay, but also instantaneously, the reduction in alveolar pressure relative to body surface pressure results in gas flow. So while this is instantaneously transitioning the drop in pleural pressure, transmitting the drop in pleural pressure to the drop in alveolar pressure, there's an instantaneous increase in gas flow from atmosphere. And so that means that pleural pressure then begins to rise, alveolar pressure, because of the increase in gas flow, alveolar pressure begins to rise relative to pleural pressure. So flow then begins to slowly decrease with time as alveolar pressure increases and approaches body surface pressure by the end of inspiration. So that's marked by the lowering of this red alveolar pressure, a lowering of the gas flow, and you can see that this pleural pressure then begins to drop in time. Gas flow decreases, okay? But the sustained decrement in pleural pressure relative to the alveolar pressure begins to increase the transpulmonary pressure. So the blue will begin to increase here. And this blue here is how much of the pleural pressure is now being dedicated to the transpulmonary pressure, or the static pressure that maintains lung volume. So then as inspiration progresses, less and less of the pleural pressure, the green, is dedicated to the alveolar pressure, and more is being dedicated to the transpulmonary pressure. So by the end of inspiration, the alveolar pressure has increased to now equal body surface pressure, so there's no more gas flow. Gas flow ceases, and the decrement in pleural pressure has been entirely invested in transpulmonary pressure by this point. So now gas flow has ceased, and now it's all of the pleural pressure is now transpulmonary pressure. So what's interesting is that the slope of this line approximates the static compliance curve of the lung. So essentially, on the Campbell diagram, this would be the static or pulmonary elastance curve, because this is volume on the y-axis and pressure on the x-axis. So this would be like a little snippet of that pulmonary elastance curve. And you can see that if this is the elastance curve of the lung, then this pressure here, the blue, is the static pressure, and that if this were shifted down and to the left or up and to the right, that is changes in compliance of the lung, the amount of blue would increase. But you can also see that this red, this alveolar pressure that is required to drive gas flow, this is an additional amount of pressure that is to the left of this pulmonary elastance curve. And as you'll see, that's how this is depicted on the Campbell diagram, an additional amount of pressure depicted to the left of the pulmonary elastance curve. So that was inspiration in a nutshell. So inspiration is an active process. Tidal expiration is passive, as the transpulmonary pressure is stored as potential energy as elastic recoil pressure of the lung. When the inspiratory muscles relax, the recoil pressure then drives expiration passively, but in the opposite direction. So now that we've understood this, both the static, which we talked about in part 1, and the dynamic properties, which we're talking about in this portion of chapter 1 of the lung, can be illustrated on the Campbell diagram. And this diagram is a graphical representation of changes in pleural pressure with respect to lung volume. And understanding this next slide is absolutely imperative before moving on to chapters 3 and 4 when I talk about heart-lung interactions, because the two key mechanical mediators of heart-lung interactions are changes in intrathoracic pressure, or changes in pleural pressure, which is depicted quite nicely on the x-axis of the Campbell diagram. And now that we understand how the pathology of changes in lung elastance, changes in chest wall elastance, changes in airway resistance, how these affect changes in pleural pressure graphically on the Campbell diagram, we can begin to appreciate in a qualitative fashion how this can affect the cardiocirculatory system, as we talk about this in chapters 3 and 4. So understanding qualitatively how the pleural pressure must change in response to these pathophysiological states is imperative. Further, changes in lung volume is also a key mediator of cardiocirculatory interaction, and that can be gleaned from understanding changes in the y-axis on the Campbell diagram. So let's turn back to our friend the Campbell diagram, and this is the static depiction of the lung and chest walls we talked about in part A, or part 1 of chapter 1. So the curve to the left of the pulmonary elastance curve represents the inspiratory activity devoted to generate airflow, and I sort of just talked about that on the previous previous slide. Okay, so you could see that this curve here, relative to this curve here, this patient would have increased resistance or flow rates or turbulent flow. So a lower pleural pressure must be generated to produce airflow for any given volume. So this would be an increase in the dynamic pressure. So comparing this point to this point, there's a lower pleural pressure must be generated. So zooming in on this aspect of the Campbell diagram, and I kind of talked about this in the previous animation, that we can see that this is a rehash of the bag and tube model of the lung. At any given volume during an inspiration, so we'll pick this, remember this is the y-axis here, so this is volume. So if we were to pick this volume at this instant in time, a certain portion of the pleural pressure, which is on the x-axis, is invested in the static pressure of the thorax, pressure of the respiratory system. And a certain portion of the pleural pressure is invested in the dynamic, and that's the red, and that's what we saw in that previous animation. And this is the recapitulation of the bag and tube model, which I've been speaking about ad nauseum. So as I mentioned previously, that expiration is passive normally and driven by the elastic recoil pressure that is stored from the transpulmonary pressure during an inspiration. So in the next portion of this chapter, we're going to talk about work of breathing, and what I'll talk about is that the triangle defined, this envelope defined by the static chest wall and pulmonary elastance curve, this triangle from here to here to here, defines the work of breathing to affect volume change. And so the expiration will be completely retained within this envelope, because all of the energy, all of the work required to generate this volume is stored in the elastic fibers of the lung. So with a passive expiration, the energy will be completely derived from the elastic recoil of the lungs and completely contained within this envelope here. But as I'm sure you've seen in the intensive care unit or in the ED or on the floor, when patients are in respiratory distress, increased expiratory resistance will lead to activation of the expiratory muscles and positive pleural pressure. So patients will grunt and bear down and force out expiration, and what that can result in is positive pleural pressures during expiration. So sometimes this expiratory loop will come outside of the envelope of the passive lung and chest wall elastance curve, and a greater increase in work will be required to drive gas flow on a forced expiration. So this would be a very positive pleural pressure. Okay. So in this final slide of part 2 of this chapter, I'm going to talk about pleural pressure variation in different disease states. This illustration is going to get a little bit wild, but I'm going to try and explain various disease states as it pertains to the Campbell diagram. So this is the normal patient, lung elastance, chest wall elastance, and this is the dynamic components of airflow in the Campbell diagram. Excuse me. So during a normal tidal breathing, airway resistance and thoracic compliance, the pleural pressure varies between about 5 and 10 below atmospheric pressure. So if you just take a deep breath in, you would follow the curve, increase in volume, and you'd go from FRC to your new lung volume. Okay? But now imagine a patient with significant reduction in pulmonary compliance, say from pulmonary edema, pulmonary fibrosis, ARDS, you name it. Pick your disease process. This is how it's represented on the Campbell diagram. The pulmonary elastance curve is shift down and to the left. Okay? So to get to the same lung volume at the end of an inspiration, just based on the static properties of the lung, a much lower pleural pressure must be generated. This is, again, saying nothing about airways resistance in this patient. This is just a patient with poor pulmonary compliance. Okay? Now I want you to imagine that the same patient is a cirrhotic with massive abdominal ascites. And so the chest wall elastance curve, because of that big ascites pressure pushing up on the chest wall and compressing it extrinsically, shifts the chest wall elastance curve down and to the right. Okay? FRC has decreased, you can see here. And at any given static thoracic volume, the inspiratory muscles must generate a much larger pressure differential in this patient. Okay? So for this volume, on the y-axis, this is the pressure that must be generated by the muscles of inspiration just to maintain this volume. And if you were to compare it to the normal patient, the curve from here to here, it's much greater. Okay? Again, this says nothing about airflow at all. So a larger portion of that static pressure is used to move the poorly compliant lung. So from FRC to the lung elastance curve, this is the amount of pressure that's used to move the lung, and this is the total amount of pressure used to move the entire respiratory system. Okay. Now imagine there's underlying COPD or airway edema causing massive increase in airway resistance. So now this patient has a large dynamic component to their work of breathing. So the pleural pressure must be even lower to generate gas flow in this patient. So that's depicted here. Okay, so this patient's in a lot of trouble. They're working hard to breathe, and I'm sure you've seen these patients who have massive ascites and pulmonary edema and maybe an underlying increase in airways resistance. So their pleural pressure must be much lower to generate a given gas flow and thoracic volume. Okay? So this red, this is the amount of pleural pressure invested in airway resistance. This is the dynamic aspect of breathing. Okay? And now if this patient has to force out an expiration, if they're grunting and bearing down because of the increased airways resistance to force air out, now they have a much increased pleural pressure on expiration. So you can see that their intrathoracic pressure excuse me, is going to vary widely from inspiration to expiration. Their work of breathing is going to be great. And as I'm sure you can appreciate, that the wide swings in pleural pressure, the wide swings in intrathoracic pressure will have very significant cardiocirculatory effects, and that's what I hope to build upon in subsequent chapters in my series. So that's the end of part 2 of Chapter 1, or part B of Chapter 1. And the next portion we will devote to work of breathing, which will flow very nicely from our now very thorough understanding of the Campbell diagram and its components of both static and dynamic airways, or static and dynamic aspects of intrathoracic pressure. Thank you.